In this video, we are going to look at the stoichiometry packet. And we're going to start off by filling in this vocabulary. And so, let's first talk about stoichiometry is the study of quantitative relationships. Quantitative. That exist in chemical reactions. We use that word, and stoichiometry can be used to determine how much product will form from a given amount of reactants. And the coefficients in a balanced chemical equation indicate the number of particles of each substance taking place in the reaction. Okay, and it is possible to interpret the coefficients in a balanced chemical equation as either the number of moles or the number of particles involved in the reaction. And the coefficients in an equation do not show the actual number of moles, only the relative number involved, and we call this the mole ratio. They do not show the actual number of moles that we are actually reacting. You must determine the molar ratio in a balanced equation before solving any stoichiometric problems. Molar ratio, and we also call this the mole ratio, same thing. And then finally, a balanced chemical equation verifies the law of conservation of matter. Conservation of matter. Matter cannot be created or destroyed. So it's important that we balance that equation to show that. All right, moving on to the next page. So we're just reading these statements, and if it's true, we're going to put true, and if it's false, we're going to change the underlined word to make the statement true. So this first one says the molar ratio of hydrogen to oxygen in this equation is 1 to 2. So if we look at this equation, our molar ratio of hydrogen to oxygen should be 1 to 2. And it's actually 2 to 1. So this is not true. This is false. And we need to change this to be 2 to 1. There's 2 hydrogens for every 1 oxygen. So if it had said the molar ratio of oxygen to hydrogen is 1 to 2, that would be correct. But hydrogen to oxygen is 2 to 1. So it was reversed. Next one says the total mass of all the reactants is equal to the total mass of the products in a chemical reaction. And this we know definitely has to be true because we must obey the law of conservation of mass. They do have to be equal. That is true. The third one says mole-mole problems involve conversions from moles of one substance to mass of another. Well, that doesn't make any sense. If we're converting moles to moles, then it involves converting moles of one substance to moles of the other. So this is false, and the correct word would be moles. And then number 11 says draw the stoichiometry flowchart. And that's that flowchart that we've been learning about. We've been using it one-sided where we have liters going in between to moles. And then we have grams. And then we have particles, which we know particles can be molecules. They can be formula units. Oh, I'm off the page here. Let's move this up. Or they can be compounds. And we've been using this chart to determine how many steps we need to make a mole conversion. So if we wanted to go from liters all the way to grams, we know we need 1-2 steps. But now we need to extend this chart to get from one side of the chemical reaction to the other. So this would be our reactant side. And now we need to have a product side as well. So I'm going to put reactants here, and then we're going to draw an arrow. And we're going to copy the same chart, but just knowing that it's going to be a different substance over here. So moles, grams, particles, and I'm not going to write out all this again, and then liters. And these are our products. And sometimes we also just say substance A and substance B. So substance A is over here, and then substance B is a different substance. So we can use this chart to figure out how many conversion factors we are going to need to make a certain stoichiometric conversion. So if we are going from liters of a reactant and we want to know how many grams of product we'll produce, we can count that would be 1, 2, 3 steps in our unit conversion. So this is a super useful chart, so make sure you have it written down and you refer back to it as you go through this sheet. Alright, let's pull that off there, moving on to the next page. So, first of all, some general steps in solving a stoichiometric problem. So first, you need to find the given value in the problem, and then you're going to write that given value down and multiply by a conversion factor. And you should set this up before you even worry about trying to figure out what conversion factor you're going to use. Just remind yourself, write the given value, multiply by a conversion factor. And if the given value is not in moles, we're first going to have to convert into moles. So that would be our first step. And then after we convert to moles, we convert to moles of the desired substance. So we first have moles of one thing, we need to convert to moles of a different thing. That's step 4. And then finally, we take our moles of our desired substance and we convert it into whatever the problem is asking for, whether it be moles, liters, or grams, or something like that. So let's look at how this works. We'll start with an easy problem. We'll do a mole-to-mole conversion. We're starting with moles of one thing and converting to moles of something else. So if we pull out our flow chart again, we can look and see we're converting moles of one thing, substance A, into moles of something different, substance B. So we know we're just going to need one conversion factor to get from moles to moles. So now let's read the problem. It says, how many moles of hydrogen are needed to react completely with 2 moles of nitrogen to form nitrogen trihydrate? Okay, so we first want to find our given value. And our given value is the part that has a number, a unit, and a substance. 2 moles of nitrogen. So that's our given value. So I'm going to write that down in math speak. 2 moles, M-O-L, and then nitrogen. When nitrogen's by itself, it's never truly by itself because it's a diatomic element. So I'm not just going to put in, I'm going to put into because this is going to be a diatomic element. So now I need to know how many moles of hydrogen are needed to react with it. And to know this, I'm going to need a chemical equation. So I've written my given value, but I don't have a chemical equation, so I have no idea how many moles of hydrogen are needed to react with moles of nitrogen. So I need to write my chemical equation. So my reactants are going to be hydrogen reacting with nitrogen, so H2 reacting with N2, and it tells me that it's forming nitrogen trihydrate, so one N and 3 hydrogens, H3. So now I've written my chemical equation, but I have to balance it so I know my mole ratio. So I notice that there's 3 hydrogens over here and 2 over there, and that's going to be hard to fix because 3 is an odd number, so there's nothing I can multiply by 2 to get 3. So I'm going to do nitrogen first. So I have 2 nitrogens on the reactant side and only 1 on the product side. So I'm going to fix that by putting a 2 here, which then that gives me 6 hydrogens. So now that's easy to fix by putting a 3 in front of H2. So now my equation's balanced, and now I can do my stoichiometry. I can figure out how many moles of hydrogen are needed to react with 2 moles of nitrogen. So nitrogen, moles of nitrogen on top. I want my moles of nitrogen to cancel out, so I'm going to put that on the bottom. And I want to get to moles of hydrogen, so I'm going to put moles of hydrogen on top. And to figure out how many moles of nitrogen are needed to react with moles of hydrogen, I'm just going to look at my balanced chemical equation. It tells me that for every 1 mole of N2, because remember there's a 1 here that's implied, for every 1 mole of N2, I need 3 moles of H2. So I can just fill that in. So moles of N2, I need 1. Moles of H2, I need 3. So now I have a nice stoichiometric conversion here. My moles of N2 will cancel out, and I'll just be left with moles of H2, which is what the problem is asking for. So this is easy. I don't even need a calculator to do this. 2 times 3 will give me 6, and my units that are left are moles of H2. So I'm just going to put moles of H2. And that's my answer to this first one. That was pretty simple. So let's move on to the next one. So this next one says how many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate into potassium chloride and oxygen gas. So I know I'm going to need a chemical equation to start doing this problem. So I'm going to go ahead and write my chemical equation. So I have decomposition of potassium chlorate. So potassium chloride, I need to do my crisscross. I have potassium and then the chlorate ion. The chlorate ion, which is, let's write it down, ClO3 with a -1 charge. And we know from looking at the periodic table that potassium has a +1 charge. So when we do our crisscross, we get K1 and only one ClO3. So potassium chloride is decomposing, so we're going to put our arrow into potassium chloride and oxygen gas. So it doesn't matter what order I write my products in. I'm going to go ahead and put O2 first because that one's easy to write. I don't need to crisscross. And potassium chloride. So it's the potassium ion again, but this time it's with just the chlorine as an element. Cl with a -1 charge. So when I crisscross, I get KCl. Now I need to balance my chemical equation. So I'm going to look at it. Potassium seems to be balanced. I have 1 chlorine on each side. So the only thing out of balance right now is oxygen. So that's going to be hard to fix. I have an even number over here and an odd number over here. So I'm going to have to double this to make it an even number of oxygens. And when I do that, notice that I threw off the balance of potassium and chlorine. So I need to fix that by putting a 2 over here. And now last I need to do oxygen. 2 times 3 is 6, so I need 2 times 3 to give me 6 on my product side. So now I have a balanced chemical equation. So let's write down our given value. So we have how many moles of oxygen, so this is what we're trying to find, are produced by the decomposition of 6 moles of potassium chlorate. So 6 moles potassium chlorate, KClO3. So let me tell you real quick, just draw your attention to the fact that one of the reasons that I chose to write my equation first is now I already know what the chemical formula for potassium chlorate is. So by writing your equation first, you already have done your crisscross. So when you're doing your stoichiometry, it's a little bit easier to just quickly write down your given value in symbolic terms instead of in writing with its full name. So 6 moles of KClO3. And then I know that I'm doing a mole-to-mole conversion. So if we look at our chart, that's just going to be one step. So I just need 1 conversion factor. I'm going to put moles of KClO3 on bottom. And I'm trying to get moles of oxygen, so moles of O2. That goes on top. And now I just need to fill in my values. And I'm just going to pull out my coefficients from my chemical equations because I know that tells me how many moles I need of one thing to react with a certain number of moles of the other. So my moles of KClO3, that would be 2. And my moles of O2, that would be 3. So this time I have 6. Well, I need to cancel my units first. Moles of KClO3 cancels with moles of KClO3. And then 6 times 3 gives me 18 divided by 2, which is going to be 9. And then my units are moles of O2. There we go. All right. Next, we have a volume-to-volume conversion. It says, what volume of hydrogen is necessary to react with 5 liters of nitrogen to produce ammonia? And so I went ahead and underlined my given value. I know that this has a number in it, it has a unit, and it has a substance, so that this has to be my starting value. And then it says what volume of hydrogen. So I'm going to circle that because that is my target substance, and my target unit will be liters if we're looking for volume. So now let's write our equation. So we have we have hydrogen reacting with nitrogen. So hydrogen's diatomic, so I'm going to put H2, reacting with nitrogen, which is also diatomic, so N2. And it's going to produce ammonia, which it tells us that is NH3. So now we need to balance this equation, because an unbalanced equation is not very useful for doing anything in chemistry, definitely not stoichiometry. And I noticed that hydrogen has an odd number. I'm going to leave that alone for now. We're going to fix nitrogen. So we have 2 nitrogens here, so I'm going to put a 2 in front of the NH3. And that gives me 6 hydrogens, so I can put a 3 over here. 3H2 plus 1 N2 gives me 2 NH3. So now, we have 5 liters of nitrogen, so we're going to write that down, 5 liters of N2. And they are reacting with some amount of hydrogen. We want to figure out what volume of hydrogen. So we're starting with liters of one thing, and we want to go all the way over to liters of a different thing. So that's going to be 1, 2, 3 steps. So I'm going to go ahead and write 3 conversion factor lines. 1, 2, 3. And then my answer will end up over here. So my first conversion factor, I need to take liters of N2 into moles of N2. So liters of N2 goes on bottom, moles of N2 goes on top. And then my next conversion factor is going to take me from moles of one thing to moles of another thing. So moles of N2 to moles of hydrogen, of H2. And then my final conversion factor is going to take me from moles of H2 to liters, to volume of H2. So moles of H2 to liters of H2. So now that I have all my units filled in, let's fill in some numbers. So we know how many liters are equivalent to a mole of a gas. So we know that 1 mole of any ideal gas is equal to 22.4 liters. So that also works here. We know that 22.4 liters is equal to 1 mole of a gas. So now we just need to look at our mole ratio to figure out how many moles of nitrogen are in my equation. That's 1. And how many moles of hydrogen are in my equation. That's 3. So we have all our numbers filled in. So now we can finish our problem up. Let's cancel some things out. Liters of N2 cancels with liters of N2. Moles of N2 cancels with moles of N2. And moles of H2 cancels with moles of H2. And we'll be left with liters of H2, which is what we wanted. We wanted volume of hydrogen. So the next thing I'm going to do is I'm going to cancel out some numbers because I have a 22.4 in the denominator and 1 in the numerator. So I'm going to cancel those 2 out as well. That makes it a little easier for me to do the math in my head without a calculator. So now I have a whole bunch of 1s. Those are easy to work with. And so I just have 5 times 1 times 3 on top. 5 times 3 will give me 15 divided by 1. So that gives me 15 liters of H2. Now box that final answer. All right, moving on to our next problem. Next we have some particle-to-particle conversions. So these conversions, if you have a particle-to-particle conversion, we're going to go from particles of one thing to particles of a different thing. So that's going to take 1, 2, 3 steps. So it says how many molecules of nitrogen are required to react with hydrogen to form 8.7 times 10 to the 24th molecules of ammonia. And so in our previous problem, we wrote this chemical equation. So we have nitrogen N2 reacting with hydrogen H2 to produce ammonia, which it told us in the last problem is NH3. So then we said to balance, we put a 2 to balance the nitrogen out, 2 and 2, and then we have 2 times 3, 6 hydrogens, so we put a 3 to balance the hydrogen out. So now let's look again at our problem. How many molecules of nitrogen, so this is what we're looking for, are required to react with hydrogen to form 8.7 times 10 to the 24th molecules of ammonia. So that's our given value, substance, and unit. So we're going to start with that, 8.7 times 10 to the 24th molecules. There's no abbreviation for molecules of NH3. And then we know, because we're making a particle-to-particle conversion, that we need 1, 2, 3 conversion factors. So I'm going to go ahead and put 1, 2, 3 conversion factors, and then my equal sign. So my first conversion factor is going to take molecules to moles. So we're going to have molecules of NH3 to moles of NH3. Then my second conversion factor is going to take moles of one thing to moles of my other thing. So moles of NH3 goes on bottom, so it cancels. And then we're converting to moles of nitrogen. Nitrogen is our desired substance. Moles of N2. And then my final conversion factor is going to take moles of my new substance to particles of my new substance. So moles of N2 to molecules of N2. So now we need to fill in some numbers. So we know exactly how many molecules are in 1 mole of any substance. And that number is Avogadro's number, 6.02 times 10 to the 23rd molecules are in 1 mole. And then once again over here we have 6.02 times 10 to the 23rd molecules in 1 mole. So now we just need our mole ratio between N2 and NH3. So NH3, there are 2 moles of NH3 in our equation, and there is only 1 mole of N2 in our chemical equation. So it's a 1 to 2 ratio. So now we can cancel some things out. We have molecules of NH3 canceling with molecules of NH3. Moles of NH3 cancels with moles of NH3. Moles of N2 cancels with moles of N2. And we're left with molecules of N2, which is what we want, molecules of nitrogen. So now I'm also going to cancel out my numbers that we have both in the numerator and the denominator. So the 6.02 times 10 to the 23rd, cancel those out. So we're left with this times 1 divided by 2. So I just need to do 8.7 times 10 to the 24th divided by 2 to get my final answer. And in this case, you might want a calculator, so I'll show you how to type that in. 8.7, and then remember we use that E button, e to the 24th, divided by the thing on bottom, divided by 2. And that gives me 4.35 times 10 to the 24th. And this does not have correct significant figures, because this answer here has 2 sig figs. This given value has 2 sig figs. My answer is 3, so I need to round. So I'm going to round 1, 2, so this 5 is going to make the 3 round up to a 4. So it's 4.4 times 10 to the 24th. And my units are molecules of N2. You do have to be very careful of significant figures in this unit, because it's important that our answers are not more precise than the values we were given originally. So now let's look at a mass-to-mass problem. So this one says, how many grams of potassium chloride are produced if 25 grams of potassium chlorate decomposes into potassium chloride and oxygen gas? So, how many grams of potassium chloride? So that's what we're looking for. And it gives us 25 grams of potassium chlorate. So we have those underlined. Now let's write our chemical equation. We have potassium chlorate. So potassium is K with a +1 charge. And then chlorate is ClO3 with a -1 charge. So when we crisscross, we get KClO3. And this is decomposing, so it's breaking apart into potassium chloride, K+, bonded to chlorine, so KCl, and oxygen gas, which oxygen is a diatomic, so that's going to be O2. So now we need to balance our equation. Oxygen has an odd number over here, so we're going to save that for later. Well, actually, everything else is in balance, so we do need to deal with oxygen. So we're going to have to double this to make it an even number of oxygens. And by doing that, we also throw off the potassium and the chlorine, so we need to put a 2 here as well. 2 times 3 is 6, so 2 times 3 balances our equation out. So now let's write our given value, 25 grams of potassium chloride, KClO3. And we're going to multiply by some conversion factors. And if we look up at our flow chart here, notice we're going from grams of one thing to grams of a different thing. So grams to grams, that's going to be 1, 2, 3 steps. So I'm going to do 1, 2, 3 steps here. Then my equal sign. My first step is going to take grams of KClO3 to moles of KClO3. Then my second step is going to take moles of KClO3 to moles of my new thing, so moles of potassium chloride, moles of KClO3 to moles of potassium chloride, KCl. And then my third conversion factor is going to take moles of KCl into grams of KCl. So now we need to fill in some numbers. So to figure out how many moles are in how many grams are in 1 mole of KClO3 and how many grams are in 1 mole of KCl, we need to look at the masses on our periodic table. So at the bottom of my sheet, I'm going to add up the masses of all my elements. So I have potassium, I have chlorine, and I have oxygen. And then for KCl, I have potassium and I have chlorine. So potassium's mass is 39.098. Chlorine's mass is 35.453. And oxygen's mass is 15.999, which we know we can round to 16. But so there's 1 potassium, so this is just one of those. There's 1 chlorine, but there's 3 oxygen, so we need to multiply that one by 3. 16 times 3. So that gives me 48. So I'm going to do 39 plus 35 plus 48. And that will give me, let's see, 48 plus 39.098 plus 35.453. And that gives us 122.551 grams per mole. Okay, and then up here, potassium and chlorine, we just need to add up 39.098. Let's see, 39.098 plus 35.453. And that gave us 74.551 grams per mole. So now we have some numbers to fill in. So 1 mole of KClO3 is 122.551 grams. And then 1 mole of KCl is 74.551 grams. And then last but not least, we need to do our mole-to-mole ratio. So moles of KClO3, that's 2. And moles of KCl is 2, and moles of KClO3 is also 2. So that is a 2-to-2 ratio. So now we need to multiply and divide out. So grams of KClO3 cancels grams of KClO3. Moles of KClO3 cancels moles of KClO3. And moles of KCl cancels moles of KCl. And then we have 2 over 2, so those cancel each other out as well. So now we just need to do 25 times 74.551 divided by 122.551. So let's put that in our calculator. 25 times 74.551 divided by 122.551. And that gave us 15.208. But in our problem, we're only given a value with 2 significant figures, so we just have to round this. The 2 makes the 5 round down to a 5, so we have 15, and then our units are grams of KCl. And that is our final answer.